Hey, what's up? I'm going to cover selection sort. It's one of the most simple sorting algorithms, probably so simple that it is rarely useful in practical terms, but it's useful in educational terms at the very least. So, in computer science, just reading the top summary in Wikipedia, in computer science, selection sort is an in-place comparison sorting algorithm. In place means that you don't have to create like another sequence, another fresh sequence to store the results in or anything like that. It can just work on a mutable structure. It has a big O of n squared quadratic time complexity, which makes it inefficient on large lists and generally performs worse than the similar insertion sort. Selection sort is noted for its simplicity and has performance advantages over more complicated algorithms in certain situations, particularly where auxiliary memory is limited. The algorithm divides the input list into two parts, a sorted sublist of item, which is built up from the left to right at the front left of the list, and a sublist of the remaining unsorted items that occupy the rest of the list. So it's just fancy for saying it moves all the sorted stuff to the front of the list, right? There's not like two separate lists really. It's just sort of like in theoretical terms talking about it like that. Initially, the sorted sublist is empty and the unsorted sublist is the entire input list. The algorithm proceeds by finding the smallest or largest, depending on sorting order, element in the unsorted sublist, or maybe in simpler terms in the unsorted list at that point, right? Exchanging, aka swapping it with the leftmost unsorted element, putting it in sorted order, basically one at a time, right? And moving the sublist boundaries one element to the right. The time efficiency of selection sort is quadratic, which is the big O of n squared. So there are a number of sorting techniques which have better time complexity than selection sort. One thing which distinguishes selection sort from other sorting algorithms is that it makes the minimum possible number of swaps, n minus 1 in the worst case. So that is interesting. Scrolling back up and looking at the stats on it, the worst case performance is n squared comparisons, but only n swaps. So if for some reason minimizing swaps is a big deal, this could be the optimal algorithm in that context. Best case performance, like if we give it an already sorted list, right, it's going to still have n squared comparisons, but it won't make any swaps. So zero swaps is a constant, I guess, is the idea there. Average performance is the same as the worst case performance. And the worst case space is constant, which is basically nothing. It doesn't use much of any extra space. And then if we go down, there's a little, oh, I guess this animation's a little bit, I was thinking of the animation for insertion sort or something else. But anyway, yeah, that's a little fast. I'm going to show you right now what it does. So using these cards, we have 1, 2, 3, 4, 5, right? So that's a little bit too sorted. Let's unsort this list by moving this one somewhere over here like this. Okay, now we have an unsorted list and we want to sort it using the selection method. Well, considering my mouse pointer is kind of like a thread of execution you could think of, so in a single threaded program, then we could only do one thing at a time here. We can only do whatever this, so if I want to move this, I can move this, but I I can't set it down like over here. So we have this list and it has five, let's say it's an array that has five, it's fixed at a length of five. If I want to move this out here, I need a variable, a temporary variable to hold it in so that I can slide stuff around and everything, if that makes sense. So I can allocate that variable and just say, like in JavaScript, var or whatever. And then I can go like this. So starting at the left, selection sort style, we say Okay, we'll say 2 is the minimum because we're doing a fresh start. So the lowest value we've seen so far is a 2. Then we move to the right. Is this lower than 2? Nope. Lower than 2? Nope. Lower than 2? Nope. 1 lower than 2? Yep. Okay, so now this is considered the minimum value, the lowest value seen so far. So now that we're also happen to be at the end of the list, we take whatever lowest value we found and then we're going to swap it into this first space. So to do that, we can just drag this over into the temporary variable. Now there's an empty space right here. So we can move this one over to right here. I guess, you know what? And then I can move this one to right here. I think if I would have made 5 blank ones and put them under there, it would make more sense. I'm going to pause the video and do that real quick. Okay, so now there's a blank spot back there, so it makes it kind of more obvious. Okay, so now the list is still out of order, right? And even if it wasn't, selection sort's still going to go through the whole thing to make sure that it wasn't. So now this one's already sorted, right? So we increment up and we start here, and then we say, okay, the lowest value seen so far is 3. Smaller than 3, nope. Smaller than 3, nope. Smaller than 3, yep. Okay, so move it out of the way, swap it with the 3, and then put that one back there. And then increment and start here. Sorry, it's so sloppy. Start here. Lowest value is 4. Lower than 4, nope. Lower than 4, yep. I think you get the idea, right? So we just keep doing that, and then we start here. Lowest value 5. Lower than 5, yep. Okay, we know what to do. And then, hey, what do you know? We have a sorted list. So that's all cool. Selection sort is, remember, it's the constant space. It has basically a linear amount of the swaps grow linearly. And since it's unstable, you might wonder, why is it unstable? Like with using that type of an example, it might not be completely obvious of what's unstable. So the definition of stable versus unstable, so you know, is that if we have something like, let's get rid of this one, let's move this over here, let's move this down here. So the definition of stable is when you have two values that are otherwise equal in value, they need to always stay relatively sorted like this to against each other. So a stable sort, the end result, this in this situation, this red 2 should always be before this black 2. In selection sort, as you could see, so we'll start here. 2's the minimum. Smaller than 2? Nope. Smaller than 2? Yep. Okay, we'll bring that down. Move the 2 over. And then put this back. And then as you can see right there, we've already lost stability, so to speak. And now it appears as though this second 2 is after this 2. The red 2 is now after the black 2. And there's no way of, without increasing the code complexity and doing, basically turning it into almost another form of a sort, to track that and make sure that it's stable. So most of the other alternatives that are this caliber of sort are considered stable. Bubble sort, insertion sort, I believe both of those are stable. Okay, so that's what's going on there. So if we jump over here to some code I've written up, it's just basically a brute force. Off the top of my head, I don't think there's another way to do it besides a brute force style of a way. I think any other way would be a different sort, right? So anyway, here's the function selection sort. It takes a list, aka array, uh, just basically a sequence of values, right? And then starting at the left, for I equals 0, blah blah blah. This is all just boilerplate, old-fashioned for loop. Then we say we set a minimum index to that I value, which over here was like basically starting right there, setting our minimum index right there, and then we move to the right to find the lowest. So this is where we nest. This is how we end up with that quadratic runtime, because for each one of these cards, we basically have to also go through the list for that card. Then for this one, we go through the list and whatnot. And even though the list is shrinking as we go, and it's like, well, hey, that's not, we're not going through the list literally a full n times n. But when you start thinking about big O, worst case, and that it's a growth complexity, so it's not necessarily about how many times exactly it goes through the list. It's about if we feed it an input that's twice as big or four times as big or whatever, how is the runtime performance going to scale against the input size? That's what's really going on. So that growth would be linear, or not, I'm sorry, not linear, quadratic. So that's why, so basically for it to be like logarithmic or something like that, it would have to be on every step, it would have to be halved. So we're not halving the problem like when we go here, we're not dividing the problem space in half. We're just like whittling it away one by one, right? So that's leaning, even, in that simple mindset, it's just leaning way closer to a linear run than it is like a logarithmic. So just remember, if it's halving at every step, like a binary search, that would be logarithmic. But if it's just basically cutting it in half one time, so if it's n divided by 2, big O n divided by 2, you drop that divided by 2, right? It's a constant, it's a non-dominant term, whatever. So that's why you end up with even if it's like, big O n times n divided by 2, we end up with just n times n, and then n times n is the same as n squared, right? Okay, so we come back over here. Then we're going to start this next little pointer, and it's going to be that second one. So while we're right here, while i's here, we're going to start j here, 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 right? And then we're going to move I up to that one, and then go j, 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 and then move I up to that one, j, j, I to that one, and j. Okay, and then after we do that, um, after we run through this thing that finds the minimum, then for that outer I, we're going to swap it. So, when that's I, that's the one that's going to get swapped potentially. When that's I, that's the one that's going to get swapped potentially, and so on. So, and we only need to swap it if that I is not the minimum. Like in this case, if we ran this one through the function, then this time, like the first pass, for instance, this would already be sorted. So when we come over here, we test and we say the minimum that we found, is that equal to I? And since on the first pass this would be equal to I and it would be equal to the minimum found, so it would just skip this swap operation in our case, because it's like, don't even bother, otherwise it would just be obviously just going like this and copying A there and then copying it right back, kind of pointless. So I would think anyway, I guess you'd have to do like a micro measurement to see on a particular architecture, particular platform, to see maybe the comparison is more expensive than the swap. I don't know. Okay, and then after it's all said and done, then we just return that modified list. So right here's console log with some sample input, and it's going to take, similar to how we had done that test by starting with the ace over here, and of course this was over there too. So that's basically the test style input it was doing. So we could see 2, 3, 4, 5, 1. That should obviously be 1, 2, 3, 4, 5. Let's hit run. Come over here and we can see 1, 2, 3, 4, 5 for the output. So it has worked. So that is selection sort in a nutshell. Thanks a lot for watching.